In this beaker we have some copper metal dipped into a solution of copper ions. At the microscopic level, there's more happening than what is appearing at the macroscopic level. So you can see that in this beaker, you're likely to find that the oxidized species, that is the Cu2+ ions, in the beaker, the blue species, the copper ions in the aqueous phase, are in equilibrium with copper metal. So this is the reduced side and this is the oxidized side, and therefore in order to become reduced it needs to gain 2 electrons. So this reaction is reversible, and if the copper metal is sitting in the solution of its ions, it's likely the electrons will just sit on its surface and it looks like there's no visible change. In a separate beaker we have some zinc metal in equilibrium with some zinc ions. And again, at the macroscopic level, nothing would be seeming to be happening. However, if we go down to the microscopic level, the zinc 2+ ions in the beaker are in equilibrium with the zinc metal. And therefore, on every metal we know that electrons are delocalized, and we're likely to have some electrons sitting on the surface of zinc metal. So this shows that the equilibrium could theoretically go in either direction. If we were to connect the two metals with a wire and a high resistance voltmeter, nothing really would be observed, and that is because even though there could be a flow of electrons through this wire here, what needs stopping it is a build-up of charge, because theoretically if the zinc has a greater tendency to give up electrons and the equilibrium moved in this direction, you get a build-up of Zi2+ ions, you get a build-up of positive charge. So in order to get to be able to measure the difference in potential between the two, we need to add what's called a salt bridge. The salt bridge is usually a piece of filter paper soaked in an electrolyte, such as a really soluble ionic compound like potassium nitrate. Potassium nitrate contains potassium ions and nitrate ions. And as you know, these are usually spectator ions, and all of their compounds are soluble, and that's important to know, that these aren't going to precipitate with any of the electrolytes in the beakers. So if they're, for example, getting a buildup of positive charge in this electrode here, in this half cell, one of these ions can migrate through the salt bridge to balance out the charge. Once the salt bridge is connected, theoretically current could flow. Now the direction it flows depends on the reactivity of the metal. So at GCSE you learn that zinc was a more reactive metal than copper, and therefore zinc has a greater tendency to give up electrons. So if you connect the two half cells, the zinc electrode, because zinc is more reactive, has a tendency to lose electrons and become oxidized. On the other hand, in this beaker here on the right hand side, the copper, because it's a less reactive metal, has a tendency to gain electrons, and the equilibrium will shift in the forwards direction and it would tend to become reduced. So naturally, if this equilibrium is moving forward and the copper is gaining electrons, the only place it can get electrons is from the zinc metal. So once the zinc atoms are stripped of their electrons and they move around the circuit towards the copper metal picks the electrons up and becomes reduced. We therefore call the copper the cathode because reduction is taking place. So if you remember red cat, that reduction is taking place at the cathode. It follows, therefore, that oxidation is occurring at the anode, so the anode is where you're getting oxidation. The high resistance voltmeter actually stops the flow of electrons, so a potential difference builds up between the two half cells, and something called an EMF, or electromotive force, is generated. This is also known as the potential difference. The two half cells, half and a half, make one, so the whole thing is called a cell. The electromotive force, if generated under standard conditions, is known as E cell, with this symbol here saying it is standard. So the bigger the difference between the two half cells, the bigger the EMF and the bigger the voltage.